Alright, good evening guys. In this video we're going to be going over problem set 3. So let's start with question 1. Show the complete mechanism for bromination of an unsubstituted benzene ring. So right off the bat we have bromination of a benzene ring. So let's draw that out. We have a benzene ring and we're going to be brominating it. Something like this. And our reagents are going to be Br, Fe, Br3. So we have an overall reaction, but we're asked to show the mechanism. So let's look at part A. Show the formation of the electrophile and use the proper catalyst. A lot of you guys forgot to do this step on the homework and unfortunately lost points, so it's important to get this down so we don't lose points for the exam. So the formation of the electrophile has to do with the Br and the FeBr3, and the reaction is going to look like this. We have Br and the FeBr3. I'm not going to draw the lone pairs around all those bromines, but just so you know they're there. We're going to draw a reaction arrow from one of these electrons attacking the iron. And what is that? What that is going to do is form this electrophile complex. Kind of like this. Again, I'm not going to bother showing all the lone pairs, but just know around all the bromines there's going to be lone pairs, and there's going to be a positive charge on this bromine and a negative charge on this iron. Some common mistakes that we found on the homework were people not drawing curved arrows for electrons moving. Just be sure to draw curved arrows because straight arrows are reaction arrows, as well as not including the charges on the bromine and the iron. So now we have our electrophile here. This is going to react with our benzene. So this benzene, one of the electrons within the double bond, it's going to come over here and attack this bromine right here. And these electrons are going to fall into this bromine right there. So what's going to happen here is that you're going to get something that looks a little like this, with a bromine attached here and a hydrogen out here and a positive charge here. So the next step is to show all resonance contributors. This is another common place where people missed points. So remember, resonance arrow, they look like this. We want to distinguish our arrows as much as possible so we don't get any points off. And be sure to draw the electrons moving in the resonance. You can go watch some resonance videos that I posted if you would like a refresher or just review some notes. And there's one more possible resonance structure, and it's going to go there. Electron is going to come over here. Positive charge is going to come over here with the hydrogen and bromine. I'm just going to put those in parentheses or brackets. And don't forget to include, I guess I forgot to include it, but I just drew the resonance structures first. The leftover electrophile complex. Br. Okay, and now we have this intermediate, and what can happen next is any convenient base, I'm just going to use B in this case, is going to come by and take this hydrogen, and these electrons are going to collapse onto the positive charge, or where there's a deficiency, eliminating the positive charge, excuse me. And just for your guys' information, this base taking the hydrogen can occur on any of the resonance structures. I just showed it here. So this is going to be your final product. Remember, for additions onto a benzene, the aromaticity is going to regenerate because it is going to be very, very stable, and that's what the reaction in nature prefers. Additionally, a lot of you guys unfortunately lost points by not drawing without including the fate of the convenient base, and this is what it's going to be. It's going to be B with a positive charge attached to the H. So this is going to be your final answer here. Okay, So now we're going to move on to question 2. Rank the molecules A through E from slowest to fastest using electrophilic substitution aromatic. So this is a very good example of understanding how the $ system works, as well as activators and deactivators. So let's start automatically with E. This is very easy, and we can automatically say this has a charge of 0. There's no activators, or not charge of 0, my bad, but I guess reactivity speed of 0. There's no activators, there's no deactivators, so it's going to be 0. Let's look at D. We have a +1 here because this is a methyl group, and this nitro group is going to be a strong deactivator, -10 for an overall of -9. So we can automatically kind of tell ourselves, okay, D is going to react slower than E. Okay, let's look over at C. We have a +1 here. We have a -1 here. Remember, halogens are going to be -1. And a C triple bond N. There's going to be a triple bond there, even though it's not explicitly shown. So if you do the math on that, this is going to be -10, which is even slower than D. Let's move on to B now. So we have here a +1 charge. I keep saying charge. +1 reactivity point. +1 here because 2 methyls. And now we have this big group over here. This is going to be a moderate deactivator. And we're just going to call that -5 for an overall speed of -3. And finally, for A, we have this weak activating methyl here, +1. And we have this right here. This is going to be a moderate activator, +5, for a total of +6. So now if we rank all of these molecules, the slowest is going to be C, and the fastest is going to be A. And then we can kind of just fill in everything in the middle, D, B, and then E. And these activators and deactivators, it is very important to memorize and know the chart. But if you guys are kind of in a pinch, a little, I guess, trick to know if something is generally an activator or deactivator is see what the first atom attached to the benzene is. So let's look at C for an example. Let's say we don't know what CN is. Is it an activator, deactivator? Let's say we don't know. The first atom attached to this benzene is going to be a carbon. Whenever you have a carbon attached to the benzene first, and then a bunch of other stuff, like in this case it's a nitrogen, typically it's going to be deactivating. The carbon in this place, I like to think of it as a wall, an electron wall. Let's look at this one, for example, B as well. Let's say we don't know what this group is. The first atom connected to it is a carbon. It's going to be a carbon, and that acts as an electron wall. So if there's an electron wall, the electrons from the oxygen and the double bond and the nitrogen and C, they can't contribute into the ring. I like to think of that carbon as a wall. Meanwhile, if you have a molecule like this one, like molecule A, where you don't know what this reactivity is in general, the first atom connected to it is a nitrogen and not a carbon. So there isn't a wall in this case, and the electrons from this overall R group, or not R group, but this overall chain can donate its electrons in. The carbon wall is not really there, so the electrons can donate into the benzene, making it react faster. Same thing with D. In this case, it's a little bit different. It's going to be a strong deactivator because the oxygens attached to the nitrogen, they have a lot of resonance on that side, which means that the electrons are being withdrawn out of the benzene ring. So that's just kind of a shorthand, little shortcut. Not really a hard and fast rule, but it's just a kind of like a ballpark. Oh, I think this is this, and then kind of go from there. Okay, now let's go to question 3. For the following reaction, give the 2 most reasonable products. No reaction is possible. So in this case, let's automatically, step 1, let's look at our reactant. We have a toluene, and the toluene has a methyl side chain, which is going to be activating. And as you guys know, activators are going to direct orthopara. So in this case, you guys should all know your nitration. We have our nitro group being added to this ortho position, as well as the para position. Alright, pretty straightforward. For question 5, draw the best resonance structure for the species below. We've been doing resonance for like a month now, or like less than a month. We've been doing resonance this whole time, so this should be pretty easy for you guys. In this case, the electrons in the double bond to the oxygen are going to go up here, and the lone pair of the nitrogen are going to swing down, giving us a resonance structure that looks like this. And you can double check yourself. Are all the charges the same between molecules? And yes, we have a positive charge on the first molecule and a positive charge on the second molecule. Resonance is not going to go away, so be sure to master resonance. So now the question asks us to circle the resonance structure that contributes more to the hybrid. Basically, both of these options are kind of poor resonance contributors. They're both pretty bad, but in this case, the second molecule is the less bad, because the positive charge is on a less electronegative atom, nitrogen, instead of being on the more electronegative atom, oxygen, in the first molecule. Alright, question 4. Draw the 2 best resonance structures for the species below. So in this case, this is another resonance question, and the place you guys want to start is on the charges. That's why I like to start. So we have this negative charge here, and let's just start moving electrons. If you guys are stuck, I would just say just move stuff around. Guess and check is kind of valid. If something doesn't work and you have like a carbon with multiple bonds, you can try, or more than 4 bonds, you can try a different route. So in this case, the electrons are going to go here, and then the electrons right here are going to swing up and form this carb anion. So we have this structure right here. We can ask ourselves, are all the charges the same? And yes, we have carbon anion in the first structure and second structure with a negative charge. And whenever you see a double bonded carbon to an oxygen, just know that these electrons love to swing upwards, because it's a very electronegative atom up here. So if those swing up, these electrons can swing down, giving you this resonance contributor right here. And then it asks us, circle the resonance structure that contributes most to the hybrid. So first order of business is to see if any one of these molecules has more bonds than another, and we see that they all have the same number of bonds, but in this case, the negative charge being on the oxygen electronegative atom is going to be very favorable. So the last resonance structure is going to contribute most to the hybrid. And then finally, what is the number of delocalized electrons? If we count how many electrons move, we have the pair that swing up from the carbanion, we have the double bond that swing up to form the carbanion, and we have the double bond that swings up onto the oxygen. That's 3 pairs times 2 gives us a total of 6 electrons. All right, thank you for watching.